HVAC 360 is brought to you today by the Tool Badger. Tired of your tools growing legs on the job site? Want to make sure that your stored materials don't pull a David Copperfield during the night? Well, it's time you get yourself the Tool Badger. Our Special Forces trained honey badgers have had a 100% success rate for the past 60 days that they've been in the field. Specially designed wristbands release a pheromone that deactivates these teeth tornadoes, turning them into docile little kitty cats. But once you leave, make sure you put back up your no trespassing tape, or you're likely to get a visit from an officer of the law. Keep your stuff yours with the Tool Badger. Rent one today. Hey, welcome back. What's up? Matt Nelson here, your host for HVAC 360, helping you be the best and the brightest in the field of HVAC. Each week, I'm either sharing information from lessons learned in the field or talking with industry experts. But I don't stop there. I want to encourage you to double down on your weekly helping of HVAC knowledge by hopping on over to HVAC360.com and joining my growing community of people just like you. All right, so what's up for this week? This week, I wanted to continue sharing information about electrical, but I wanted to take it in a little different direction, namely controls power. Now, there's a little bit of difference when we talk about controls power versus normal power. Controls power typically is run, it's run by an electrician, but it's run by an electrician that is under the temperature controls contractor. So typically you'll have your HVAC contractor, your electrical contractor, and underneath your HVAC contractor, typically you're going to have your temperature controls contractor. They will have a subcontractor that is also an electrician. Now, you'll find some jobs when that is the same electrician as the primary electrician on the job, and sometimes it will be different. But there will be a specific person running that low voltage wiring, a specific contractor running that low voltage wiring for the temperature controls contractor. Typically, they're not turning a screw. You know, that's one of the things that they do. They'll have all the equipment together, they'll program it, but they rely on the electrician that is their subcontractor to kind of put it all together. So, what are we dealing with here? There are what we have line voltage controls. Those are typically, and we've talked about those before, those are for standalone, simpler devices, control devices. And there's really, these are more prevalent in a place that lacks a building automation system. But that's not what we're talking about here. So those are line voltage controls. We're talking about low voltage controls. And, typically that's going to be a 24 volts. Now, I did some digging, similar to what I've done in the past for the electrical, to kind of figure out exactly, where did this 24 volts come from? And you know what? I really didn't. There's a couple of different things that combine for it to make sense a little bit. So a couple of things like this. Typically, when we're transforming down from line voltage, that's 124 volts here in the U.S. So 124 volts, if you divide that by 5, and that's a ratio you can do with a transformer. So if you have one winding versus 5 windings, you can get the 120 volts down to 24 volts. So mathematically, it makes sense there. Another thing that really pops up is the fact that a lot of times you're transforming to a 24 volt DC signal. Now, I guess when you're transforming the 120 volt AC down to a 24 volt AC, that's different than a 24 volt DC, and that's where things get a little bit confusing. But if you look at most of the standard car batteries that are out there, those cars are operating at a 12 volt DC system. Now, there are some larger trucks out there. You get a little bit bigger. They're going to have 2 batteries, and so they're actually operating on a 24 volt DC system. Now, why 24 volts? 24 volts, I guess, is considered low enough to be considered safe. I'm gonna pause right here because, again, just like with the electrical, I'm a mechanical engineer. These are things that I've been finding out through my research, and I want to help you out on your journey of learning. So I want you to take all this with a grain of salt and use it as a stepping point for your learning journey. So I'm just telling you the best that I can, and I want to kind of start the conversation. So again, the 24 volts is considered low enough to be considered safe, and I'll use that in air quotes, safe, because really anything can be dangerous in the wrong situations. So, but it's high enough to really do useful work with currents that are practical. So you get that differentiation there. You don't want to be too low, but you want it to be high enough. Similar to what we were finding out with the electrical. Why did we have 60 hertz? 60 hertz was high enough to be useful for lighting, and then also low enough for the motor loads. So it was a kind of a convenient middle ground. So the one thing too is that if you're using a like a 24 volt system, you could use a 24 volt DC battery. Because those are used in cars, but you can use that standard battery, parallel a couple of them, and you'd get a 24 volt DC signal, and you could use that as a backup for a UPS or an uninterruptible power system. So it allows for moderate amounts of electrical noise. So typically when you're dealing with a voltage, you don't want it, when you get down to a lower voltage, there are things that cause noise, and the 24 volts allows this to be just kind of in the sweet spot. So it allows it for a little bit of electrical noise, but not too much, and it still can stand out. All right, so what do we see in the field? Typically, we're going to see that the panel. So we're going to have the temperature controls panel, and typically we have that 120 volt power connection. Make sure that you have, when you're checking your drawings, make sure that you're having and coordinating that electrical power for your panel, for your building automation system. Also, while you're at it, why don't you coordinate to make sure that you have the data drops so you can coordinate that with your data system to get that on the network. Very important things. You're going to have that power connection, and you're going to have, I guess, two things there. You're going to have a transformer, like a little internal transformer that in some of the panels is going to transform it from the AC to the 24 volt DC signal, and it's going to supply the different components of that temperature controls panel. And you're also going to supply typically they have a 120 volt AC plug adapter. So anytime you need to do any sort of maintenance, you can plug certain tools in there so you can get the power from the panel in and of itself. What else are you going to use, outside of the temperature controls panel? Well, typically there's going to be transformers. There may be transformers out in the space. Transformers could feed VAV boxes. So if you have VAV boxes that require power, they might be linked to a common transformer. And again, your transformer is going to be limited by the number of devices it can serve. But again, that's where you want to coordinate your locations of your boxes with your electrician or your electrical engineering counterpart to make sure that their design is going to be adequate for what you're trying to do. You could also have transformers in VAV boxes. That's a lot of times if you have like electrical heat in a VAV box, you're going to have a transformer right in that box. You might even have more than just 120 volts going to that box, depending on the size of the toaster coil that you have in there. So I just wanted to kind of lay that out there. So those are some of the uses that you're going to have with your AC power, different spots that it's going to go to. Just want to keep it simple. Now, I guess there are a couple of different things. So where are some of the other voltages, all of these ranges? And one of the things I wanted to do, not only talk about the 24 volts for the power, but I wanted to talk about the different ranges, the inputs and outputs that you're going to see. And a lot of these are analog values that you're going to be using. And when you're talking controls, typically you're going to have digital values, so binary, 1, 0, on, off, yes, no, that kind of thing. And then there's going to be a set of analog values. So that is going to be, analog voltage, analog current, and that's going to give you a range. That's going to give you feedback. Anything that's going to change or vary is going to be an analog value. So typically what you'd use, way back when, is you'd have pneumatics. So pneumatics typically, and pneumatics, just to kind of give a flavor for where that was, pneumatics, you would usually use that in a 3 to 13 PSI range, and typically that was split up between typical spring ranges. So they'd have like a 3 to 18 spring range, they'd have a 5 to 10, and they'd have an 8 to 13. And what that would do is, depending on what control pressure, pneumatic pressure that you sent out to the system, your devices would react a certain way depending on what their spring range was and what the pressure was. So it would vary. And when you look at it, you have about a 10 PSI spread, from the top to the bottom. So that was, a 10 PSI spread. That was pretty good. And that was what they would use. And a lot of that kind of carried over when we're talking about, different things on the electrical side. Now, they could still have, a combination of electrical and pneumatics. They'd use these EP transducers, and what that would do is that would take an electrical signal and it would create a pneumatic reading. Pneumatics are great, I guess, in general. You typically see them in older systems. You typically see them in systems like central plants, and the reason for that is, especially for the central plants, is because you're dealing with larger valves. You can do a lot more with air pressure than you can do with the small electrical voltages that you're using. For most things, especially on the the typical sizing on the HVAC side, they work great. But when you look at the larger valves, you really need a lot of torque. And what happens is you end up having to have a lot of actuators, multiple actuators on a single valve to be able to turn it. So pneumatics was great in doing that, and they could handle that, rather easily. Obviously, there was downside with pneumatics with leaking and being able to trace the system. So there's pluses and minuses to everything. When you looked at analog voltages, now we're going to get into the kind of the controls aspect of the electric side of it. It's kind of split into two different categories that I'm going to talk about, and I'm going to kind of leave it simple here. So you have the analog voltages and you have the analog currents. Now, the analog voltages, whenever you hear about people talking about, 0 to 10 volts DC, that's what we're talking about. That's an analog voltage. And that's something that's very typical. It's widely used, very common. You can even, they even come, as far as like inputs go, 0 to 1 volts DC, 0 to 5 volts DC, or as far as outputs go, you see a lot of 2 to 10 volts DC. So that's all kind of based on that 0 to 10 volt analog voltage. So it is a very standard, widely used, very common. The downsides is this: the motors, relays, and other noisy power supplies can really introduce interference that degrades the signal. So when we're talking about the 24 volts being large enough to avoid some of these noises, a lot of the simple 0 to 10 volt DC, which is implemented to kind of, again, echo that 10 psi spread on the pneumatic side, so it would match up real great with that. The downside was that if you used it for certain things like motors and relays or some other noisy power supplies, you could get a situation where the signal wasn't real great. And they were also susceptible to voltage drops over long distances. Again, you realize, when we talked about the difference between AC and DC in the power distribution system, you notice that the one downside to the DC system was the distance. It just couldn't, you'd have to have a generator station every mile to be able to get it to, the local houses, whereas an AC system could go much, much farther. The same thing holds true when we're using voltage, DC voltage, on the control side. It's very susceptible to long drops, so you're really not using it a lot for long cable runs. You're gonna find it problematic. Now I know there's a lot of references in there because when I did some digging, trying to find out the 0 to 10 volt DC. A lot of that is used in dimming and lighting controls. The one thing that I found out is that there is a separate power supply to an instrument. So 3 wires are required. So what that means is that you can control with 2 wires, but you're going to have a separate power feed to a device. So that's going to add a little extra complexity to the system. Now, on the flip side, when we talk about analog current, this is where you see the 4 to 20 milliamp system. That's going to be either input or output, 4 to 20 milliamps. And you notice that, if you took it to, 0 to 20 milliamp, you could know that, if you talk about the 0 to 10 volt DC, that was just, you basically double the 4 to 20 milliamp. So the signals, they could scale together, so they could be, the same thing. The one nice thing about the 4 to 20 milliamp is it doesn't really have the same problems with the noise because you're not using that voltage. You're not using you don't get that interference from motors, relays, and those noisy power supplies. Another bonus is that you have a positive zero position. Now, what do I mean by that? Because we use the 4 to 20 milliamp, excuse me, rather than a 0 to 20 milliamp, the 4, when we're feeding it power at 4 milliamps, that equates to 0 in a device. So if we don't get, the 0, if we don't get 4 milliamps, if we're not detecting that, and we're getting 0 milliamps, we know that there's something wrong with the system. Now, typically, you're going to be a little bit more costly than, I noticed there was a cost difference between the 0 to 10 volt DC and the 4 to 20 milliamp kind of devices, but that's really becoming more and more a non-issue as 4 to 20 milliamps becomes cheaper. A lot of the devices that you're going to be finding in a controls panel can do both the 0 to 10 volt DC or the 4 to 20 milliamp side. So there's a lot more complexity there, a lot more detail that you could really get into if you wanted to. But I just wanted to kind of, overall, just kind of cover that. One last thing about the 4 to 20 milliamp analog current is that the instrument can be loop powered, so often at the 24 volt DC, which means it can be supplied by the same cable that it transmits on. Again, you're down to 2 wires, so what you're doing is you're providing a voltage which is giving you the power, but the milliamp signal is separate. So the milliamp is actually transmitting the information, and you have voltage on that same line providing the power. So it's a little bit simple. And obviously, if you're interested, you have more questions, certainly give me a holler. Let me know. But I just want to kind of go over some of those basic things with the analog voltage, analog current, and a little bit about 24 volts, where did it come from. All right. Well, that's it for this week. Thanks so much for listening. I hope it was helpful. If you know anybody who's looking for more information about this topic, consider passing it along. If you're not a subscriber, consider joining the growing community of people like you over at HVAC360.com. And I'd be greatly honored if you'd leave me a rating and review on Apple Podcasts. It really helps people find the podcast and spread the word. Also, everybody knows, or I want you to know, that we're also on YouTube. So each of these episodes is published on YouTube, some of the newer ones. So if you can go over there and hit subscribe, I greatly appreciate that. It really helps getting started, getting the minimum number of subscribers on YouTube really gets me into that next step, and allows me to do some fun things on YouTube. Well, that's a wrap for this week and this episode of HVAC 360. I'm Matt Nelson, helping you be the best and the brightest in the field of HVAC. And as always, know what you build and share what you know.